one, we may start. Let's see. It's my great pleasure and great honor indeed to introduce Vern Paulsen from University of Toronto, who's going to give us the last colloquium of this long focus program on factorization and RKHS. Vern,
Thank you.
please.
Thank you, Javad. It's Waterloo, but close enough. And as always, you're much too kind and flattering in your introductions.
Thank you.
So what I'd like to talk about is some applications of reproducing kernel Hilbert spaces to a kind of factorization problem. So let me, okay, there we go. Let me start with the overview. So I think it's pretty well known that if you have a positive semi-definite matrix, or even a positive semi-definite operator on L2 of the natural numbers, then these can always be factored as a lower times an upper triangular, or an L star factorization. And if you have just a matrix, then it also can be factored as upper times lower. But generally, when you have a bounded operator on L2 of the natural numbers, it can't be factored as an upper times an upper star. And at the time we did this, there wasn't really a clean theory for determining when an operator does have such a factorization. However, we'll see that these upper-lower factorizations are more natural from a function theoretic point of view. So it's not, so there's some good motivations for wanting to do this sort of opposite of the natural factorization. And there's now a nice theory about when operators do have UL factorizations. And the key trick was to attach a reproducing kernel Hilbert space of analytic functions to each positive operator. So that's what I want to go through today. I want to talk about some very old things where this was done, dating from the 90s, these two papers with Greg Adams, Paul McGuire, and then later with John Froelich as well. And then a somewhat more recent extension of some of those results, which I did with Hugo Werdeman just a couple of years ago. And then at the end, I want to talk about some future directions that are still open. There's some relations of this theory to Caddis and Singer, and to some open questions in several complex variables. Okay, so let's get the ball rolling. I'm going to assume most of you know about this Cholesky algorithm. So if we're given a positive semi-definite n by n matrix, sorry, I thought I had that on mute. Then if you apply one step of the Cholesky algorithm, you can always get a rank 1 positive. So you decompose P as a rank 1 plus something which is 0 in the first row and column. And so I like to think of this rank 1 as a column vector. And then if you apply Cholesky to this second matrix, again, pivoting on the 2-2 entry, that gives you a column vector that's 0 in the first entry. And then after you subtract that, you'll have something which is 0 in the first 2 rows and columns. And continuing that way, it allows you to decompose P as a sum of rank 1 positives, where each one of the column vectors defining the rank 1 positive is 0 in the first I-1 entries. So if you just stack those column vectors in as the columns of a matrix, that matrix will be lower triangular. And if you calculate L times L star, you get P. So this is something that's often taught in undergraduate linear algebra courses. So this is the proof that everything has an LL star factorization. If we had a bounded positive operator on L2 of the natural numbers, we could repeat this same process. So I always think of operators as matrices indexed by the index set. And we get this sequence of vectors so that this sum, CN star, converges. You don't have to worry too much about how the convergence, just that it's entry-wise by entry-wise convergence. And if you let L be this formal matrix that has Cn for its nth column, then you see you can do the matrix multiplication of L times L star, and it gives you Pij. So that proves that the L you get this way is a bounded operator. And so we get a lower upper factorization of every bounded operator on L2 of n. So if we go back to this n by n case again, if we did the Cholesky algorithm, but instead of starting with the 1, entry, we started with the NN entry and worked our way backwards, then we'd get P written as a sum of rank 1s, where the rank 1s would be 0 in the last I-1 entries. So again, if you stack them in as columns, you'll get an upper triangular matrix. I just need to reverse the order that I put the columns in. I'll get an upper triangular matrix, and U times U star will be equal to P. So that's the proof that, that's one proof that every positive can be factored as a UU star as well. And the key thing I want to stress here is what I had to do is start with the last entry. And of course, if I have a bounded operator in little L2 of n, there is no last entry. So this gives no immediate way to do a UL factorization. And so a priori, it's not clear if every positive operator does have such a factorization. So, so now let me return to why should I care about upper times lower factorization so much? And the answer really comes from function theory. So I want to go back and think of, instead of the natural numbers, let's just think about the non-negative integers. So that I can identify L2 of Z plus with the Hardy space by the nth basis vector corresponds to Z to the n. And also we identify the Hardy space with the subspace of square interval functions on the unit circle. And then I want to look at the classic theory of Toeplitz operators. If we take a bounded measurable function, we always have a bounded multiplication operator on L2. And the Toeplitz operator is just the operator you get by restricting to the Hardy space, followed by projection onto the Hardy space. If we factor the symbol G as F times H bar with F and G analytic, then what that does is that factors the Toeplitz operator as TH star times TF. And notice it's not the case that you can do this in the other order. It's not equal to TF TH star. But notice that since F and H are analytic, H star is upper triangular and L is lower triangular. So, so when you want to do factorization of symbols and you want to look at the corresponding Toeplitz operators, the factorization of symbols into analytic and co-analytic parts corresponds to UL, but not to LU. So now let me remind you about the Zago alternative. It tells us that if we have a positive function on the circle, then G can be factored as mod F squared for an analytic function if and only if G is log integrable, and only if this integral is larger than minus infinity. And what we showed in this paper is that, well, if you could factor TG as UU star with U any upper triangular, then without loss of generality, U may be taken to be, well, I should say co-analytic Toeplitz. U star is the analytic one. So if you can do an upper triangular factorization at all, upper lower, of a Toeplitz, then you could have done an analytic one. And so, so this tells us right away that T sub G factors as a UU star if and only if the symbol is log integrable. So this shows us that this at least gives the first an example of things that don't factor. So on the other hand, we also see that some things will factor, because if G is log integrable, then it does have such a factorization. So, so this shows that the world separates into things that factor and things that don't factor. So the question was how to build a nice theory of which things do and which things don't. So the approach that was around classically was to start with your matrix for your operator and think of partitioning it into, this is the first n by n corner, and then this is everything else. And then because Pn is finite, it has a last entry. And so it can be factored as a un star, where this is just n by n. But then you could look for criteria that if you think of these UNs as infinite matrices by just filling them out with zeros, you'd like to try to do some special factorizations so that these UNs will converge as n goes to infinity. And this is generally what was meant by reverse Cholesky algorithms. But it was very hard to find necessary and sufficient conditions for when you could arrange to make these UNs converge to something. So the better approach was to use the theory of reproducing kernel Hilbert spaces. So I'd like to show you the ideas there. So this is a fairly classical idea that every time we have a matrix that's positive semi-definite or operator, we can attach a power series to it, Pij z to the I, w bar to the j. And it's easy to show that this converges on the disk to be an analytic co-analytic function. And it's not too hard to show that what it converges to is actually a positive semi-definite function on the disk. So it gives rise to a reproducing kernel Hilbert spaces of analytic functions on the disk. And so I'll always denote that space by h of k sub p. So to each positive, we've got this reproducing kernel Hilbert space where this is our function. It has a fairly nice description. This idea goes back to Saracen, really. If you factor p as xx star with the x a bounded operator, then you can prove that a power series belongs to this space if and only if the vector of coefficients is in the range of x. Of course, this implies that no matter how you factor things, the range of x, if you also factored it as yy star, then the range of x must be the same as the range of y. And that's the classic Douglas factorization theorem. That if xx star equals yy star, then the range of x equals the range of y. So independent of how you choose x here, you always get the same range. And that range space is exactly this reproducing kernel Hilbert space. So this is just setting up the dictionary for going back and forth between positives in these spaces. And so then our key theorem, which appeared in the next paper, was that if you have a positive semi-definite operator, then it does have a UU star factorization with U upper triangular, if and only if the polynomials are dense in this reproducing kernel Hilbert space. So that gives us a sort of canonical way to decide if we have factorization. The idea of the proof is pretty simple. If your P does factor as a UU star, and you look at this sum for each fixed n, you look at some u I n z to the I, that'll only be a polynomial because these i's are all 0 once you get past n. And you just check that the fact that P equals UU star means that as power series, KPZW is the sum of the PNZ, PNW bars. And if you've looked in my book, the book with Raghupathi, Anytime you have, it's fairly well known that if you have an orthonormal basis and you do this sum, you'll get the kernel function. But conversely, if you have a set of functions which add up to the kernel, then that set of functions is what we call a parsable frame for the Hilbert space. Oh, excuse me. It's allergy season here. But in particular, a parsable frame is the linear span is dense in the space. So that shows that the linear span of the polynomials is dense in the reproducing kernel Hilbert space. And so that shows if you can factor, then the polynomials are dense. Conversely, if the polynomials are dense, then you can choose an orthonormal basis of polynomials. And if you use their coefficients, those will give you finitely supported column vectors. And if you just intersperse them with 0 vectors if needed, you can make those column vectors stack up to give you an upper triangular matrix. And then the fact that the sum of the QNZ, QNW bars adds up to the kernel function guarantees you that matrix U satisfies U star equals P. So the theorem was not difficult to prove. But it also gives us a pretty lovely theory of how things behave. So let me call a positive operator completely non-factorable if anytime an upper triangular is dominated by it, then that upper triangular has to be 0. And then the final theorem is that if you have a positive operator, then it always decomposes uniquely as a sum of 2 positive operators, where the first one factors as a upper star, and the second one is completely non-factorable. So this theorem would be really hard to prove without the reproducing kernel Hilbert space approach. But with the Hilbert spaces, it's really quite simple because you just take your Hilbert space. If it has any polynomials at all, you can look at their closure, and that gives you a subspace H1. And then, so H1 is either a nice space or it's just 0, and you take H2 to be H1 perp. Then that gives you a decomposition. And each of these subspaces will be reproducing kernel Hilbert spaces. So they'll have kernel functions. And you can show those kernel functions. They have to be analytic, co-analytic. And so they have expansion as power series. And that gives you 2 matrices, 2 operators, P1 and P2, which add back up to P. Because they're positive and add up to P, they're both bounded operators. And then because the polynomials are dense in this first space, it does factor. And then you use the fact that H2 contains no non-zero polynomial to prove that P2 is completely non-factorable. And that's roughly because if you have a UU star, which is less than P, then each column of U would give you a rank 1 positive, which is less than or equal to P. And that rank 1 positive corresponds to a polynomial. And that if we were less than P2, then that polynomial would belong to H2. So that polynomial must be 0. So if you have a UU star that's less than P2, each of its columns has to be 0, and so U has to be 0. But this leads to a new version of the Zago alternative, and that's that T sub G factors as a UU star, or T sub G is completely non-factorable. So when it's log integrable, this happens. When it's not log integrable, the symbol actually has to be completely, the triplets operator has to be completely non-factorable. So those give rise to reproducing kernel Hilbert spaces that contain, of analytic functions that contain no polynomials. Using this idea, we were able to extend on this Zago alternative a bit. And you can prove the following. So we've got the classic log integrability is the same as mod f squared. That's Zago. And we saw that's the same as this analytic turplets factorization. And we saw that's the same as a UU star factorization for any old U. And then we're able to add two new things in terms of this reproducing kernel Hilbert space. That's that multiplication by Z is a bounded operator, a multiplier of this space. That turns out to happen if and only if log G is integrable, or the fact that the constant function 1 belongs to the space. That's if and only if log G is integrable. So we have, in terms of the reproducing kernel Hilbert space attached to the turplets operator, we get these two new versions of the Zago alternative. Okay. Well, to keep the presentation simple, I stuck to the single variable case, but everything we did here applies to multivariable. We just need to set up the notation correctly. And so here's the way to think of things. I'll talk about multi-indices as tuples of non-negative integers. And if I have a multi-index, I can think of that as a monomial on the polydisk, where I'll write z to the I when I want to do z1 to the I1 ... times zn to the in. And we know those are an orthonormal basis for the multivariable Hardy space, H2 of dn. And similarly, if I want to look at the tensor product of this space, it's got an orthonormal basis, which are the tensor products of the orthonormal bases. And I'll use multi-index notation there too. When I want to do EI1 tensor EI2 ... I'll just write that as E sub I. And we have this natural isomorphism is just sends the E sub I to the Z to the I. And so if you have a positive operator on this tensor product space, it has a matrix by just, you do P applied to E sub capital J inner producted with E sub capital I. We can't really order these so well anymore, but we can still think of it as a matrix. And we can still define a power series on the polydisk by Pij of Z to the I, W bar to the J. And everything I said before holds. This is a kernel function for reproducing kernel Hilbert space of analytic functions on Dn. If we factor, then a power series belongs there if and only if AI e to the I is in the range of X. And now I want to talk about the analogs of LU or UL factorization. And so first I need a definition. If I have a matrix UIJ, I'll say that it's N upper triangular, provided that the only time UIJ is non-zero is if IK is less than JK for all K. So if you like, this is a partial order on the I's and J's. I know some of you are familiar with nest algebras and tensor products of nest algebras. And the original case I was doing with U little I little j being upper triangular, that's one of the nest algebras. And this is a tensor product of nest algebras. And then what our theorems say in this case is that P factors as UU star with UN upper triangular if and only if the polynomials are dense in this multivariable reproducing kernel Hilbert space. Every P decomposes uniquely. There's a P1 plus a P2 where P1 factors and P2 is completely non-factorable. And moreover, the proofs are identical to the proofs I gave in the single variable case. So there's a nice theory this factorization with respect to this tensor product of nested algebras that we worked out in the 90s. The other topic I'd like to talk about factorization has to do with banded operators. So a matrix is called banded if there exists an M so that aij's are 0 whenever I minus j is bigger than M. In this case, M is called the bandwidth. And it's a classic result that banded operators always have UU star factorizations. And then there were some generalizations of this where the width of the band was allowed to grow, maybe say linearly as J grows or something. And then people were able to extend this factorization result to more general classes of banded. Then in the work with Hugo, we were able to do sort of the most general case of what you might call banded. And it's referred back to this, this stuff in the 90s. And the key result was some new results on the structure of these reproducing kernel Hilbert spaces that involved differential operators. And so what we showed with Werdemann is if we have some positive operator here, and we look at the corresponding reproducing kernel Hilbert space, and we look at a multi-index, and we think of the differential operator that's the partial derivatives. So in the Z1 direction, you take J1 partials, ... Zn, you take Jn partials of this analytic function that's in this space, and you evaluate at 0, then those turn out to be bounded linear functionals for no matter for every positive operator. And so that means they're in a product with some, well, sort of kernel function for this differential operator. And what we proved is that these give you another spanning set for your reproducing kernel Hilbert space. So not only are these bounded, but they span the space. And then using these two results, we were able to show if you have any even multivariable operator, such with the property that for each fixed j, Pij is non-zero for only finitely many j. So that's sort of banded in the weakest sense, right? Along each row, you're finitely supported. Then that's enough to guarantee UU star factorization with U n upper triangular, or upper triangular in the one variable. And the proof is quite simple. What you do is you show that these phi j's, anytime the P is banded in this sense, then these phi j's are actually polynomials. And so you know the polynomials are dense. And there were also several factorization results about tensor products of nested algebras, which we realized were really consequences of this work going back to the 90s. So that was the other part that was in this paper. So that sort of brings us up to date with what we know about this factorization. And for the sake of simplicity, I've kept to the case that the entries of these matrices are always scalars, but the theory we did, all these theorems are true if the entries are really bounded operators on some other Hilbert space C. So instead of just looking at L2, say, you're looking at L2 tensor C. And in that case, this space is really a reproducing kernel Hilbert space of analytic C-valued functions. And everything I've said has NLogs in those cases too. But wanted to keep things as clean as possible for this talk. Okay, so let me talk about some directions for future research. This was actually things we'd planned to do back in the 90s, but all of us got sidetracked one way or another. And that's really the main thing that I think is interesting here, are these looking for multivariable NLogs of the Zago theory, the Zago alternative. So you'd like to start with a positive function on the N torus, and you'd like to know when you can factor it as mod f squared with with f analytic on the polydisk. And there are lots of examples that were given in the early days, especially Rudin and Rubel, that showed that if your function was just log integrable, that's not sufficient for factorization. And they even proved much stronger things were not sufficient for factorization. So so here are the problems we were interested in. So the first one is in the one variable case. We proved that if a Toeplitz operator factors as UU star, then necessarily the U's could be taken to be Toeplitz operators themselves. But we could never prove the analog in the multivariable case. So suppose you have a Toeplitz operator and it factors as UU star with you know, the correct analog of multivariable Toeplitz are these n uppers. And we could not show that that implied that it had a Toeplitz factorization. And so we couldn't show that that implied that it had a mod f squared factorization with f analytic. So we still don't know the answer to that. And one reason that this might be good is it's possible that the answer is no, in which case, you know, maybe you can't do analytic factorization, but maybe the right question to look at is whether you can do n upper factorization. And so, so that leads to the following problems. Maybe even though it looks hopeless to characterize the functions that have mod f squared factorizations, maybe a more natural question is to characterize the Toeplitz operators that have UU star factorizations. So I'm talking multivariable here. And then the other thing is, in terms of the reproducing kernel Hilbert space, we were able to give several equivalents to the Zago alternative. So the other natural equivalents would be, can you characterize the symbols for which they're invariant under multiplication by all the coordinate functions? We know in the single variable case, this is another equivalence to the Zago alternative. So maybe this is the right question to ask in the several variable case. And then we also saw that the identity function belonging to the space was equivalent to the Zago alternative. So maybe this is the natural question to ask in this case. So I think there's possible room for making progress on this sort of hopeless task of analytic factorization, but maybe it should be answering some of these other questions, which in the one variable case are equivalences of the analytic factorization. And then the other direction involves things to do with the Kadison-Singer problem. So there was a lovely work by Nikolsky. Well, let me back up a moment. The Kadison-Singer problem was shown by Kazaza to be equivalent to this thing called the Feichtinger conjecture. The Feichtinger conjecture is about these things called frames, which are sort of a generalization of respaces. And so there's a statement about behavior of frames that's equivalent to Kadison-Singer. And what Nikolsky did is he looked at the Hardy space, and he looked at point evaluations, so the kernel functions for points. And he said, okay, suppose we have a set of these that forms one of these frames in Kazaza's sense. Is the Feichtinger conjecture true in the setting of the Hardy space, where all the functions we're getting are coming from these things which are frames, which is sort of a very close analog to sampling sequences. And he worked out very carefully what the Feichtinger conjecture said in that case. And he was able to prove for the Hardy space and sequences of these sort of generalized sampling sequences that the Feichtinger conjecture was true. But his proof used the full power of the Carlson theory. So Katterson-Singer specialized to sampling sequences, turns out to show it's true in the Hardy space, turns out to be need Carlson's theory or use Carlson's theory. So what we did in this paper with Latta, we showed that if instead of doing just the Hardy spaces, you did these H case of P spaces, and you ask this same question that Nikolsky was asking. You took sampling sequences in these, and you ask if this thing held for these. Then this was a large enough collection of spaces that the converse was true, that if you could answer this sampling sequence space in all of these, then that was equivalent to Katterson-Singer. Well, in the meantime, Katterson-Singer has been solved, but it's been solved by completely different methods. These methods involving sort of algebraic geometry techniques and questions about moving around zeros of polynomials. But because of this paper, we know that Katterson-Singer is also equivalent to some statements about sampling sequences and reproducing kernel Hilbert spaces. So there should be a deep connection between this proof of Katterson-Singer and things going on with sampling sequences and reproducing kernel Hilbert spaces. And it should be stuff that's even more powerful than Carlson, because Nikolsky needed Carlson to just do the case of the Hardy space itself. So I think that's another fascinating direction, is now that we know that these statements about sort of generalized sampling sequences are true for all these spaces, there must be some deeper Carlson type results that come out of as consequences of these new Katterson-Singer approaches. Well, so that's where I'll end. Sorry, it's a slightly brief talk, but it spans a quarter of a century of mathematics in some sense, with a long gap in between. And I hope that maybe some people will pick up the torches on these two problems that I think I've been fascinated by for a long time, and I think are really ripe for extensions. So I'll end here. And as I said, these directions have not yet been pursued on any of these kinds of problems.
Thanks a lot, dear Vern. Let's thank Vern first for this wonderful talk. Any question or comments for Vern? Since I do not see you all, if you have any question, please go ahead. Indeed, Vern, myself, I have a question. When at the very beginning, when you talk about Cholesky factorization, you emphasized even twice that we start from the last entry. I mean, why?
Oh, so if we want to do the lower upper, we start at the first entry. But
Okay.
when you want to do upper lower, it works if you start at the last. So when you start with the last entry, the first rank 1 that you removed now gives you a matrix which is 0 in the last row and column.
Mhm.
So now you move to the n-1 entry and do Cholesky, and you'll get a column vector that's 0 in its last entry. So if you want to build yourself an upper triangular matrix, you're going to take that first column vector and you'll make it the last column of your matrix. You now have a vector that's 0 in the last entry. So if you put it in as the next to the last column, you'll be upper triangular.
Mhm.
So it's the point is, when you do Cholesky starting with the last entries, you get vectors which are 0 in their last entries, right? And so when you're 0 at the bottom of a vector, that's when you can stack it and make it upper triangular if you put them in the right order. Whereas when you do Cholesky starting at the first entry, you get vectors which are 0 in their first few entries. And if they're 0 at the top, no matter how you arrange them, you can't turn them into an upper triangular matrix. You can only turn them into a lower triangular.
That's true. Yeah.
Whereas when they're 0 in the bottom entries, if you list them in the right order, you get an upper triangular.
Mhm. I got sensitive about this because at some point in your book, you say that due to, I mean, numerical analysis restrictions, sometimes we choose the biggest one, the largest one on the diagonal, and we divide by that and start from that column and row, and then we proceed. So, but that's another story.
Yeah. When numerical analysts want to do this decomposition into rank 1s, it's more stable if you use the ordering of choosing the largest entry at each step.
Okay. Thank you.
The main reason is if your diagonal entry is a very, very tiny number, remember you have to divide by that tiny number, and that's numerically unstable.
Further question or comments? If not, let's thank Vern again for wonderful talk.
I hope you're not disappointed that the fireworks show was late for the short for the grand finale.
That's wonderful. That's
I think
wonderful.
often grand finales are supposed to run over.